There we go.
Okay. Our next presenter is Greger Ottosson, who already presented in day one. And as I told you previously, Greger is responsible for applying AI to decisioning products in IBM. And as you noticed, there were a lot of discussions related to explanations of decisions, especially when the decision made together with rules-based systems and machine learning. And it would be really interesting to hear from a major vendor who applies both technologies to real-world applications. How do they explain decisions? And hopefully we all can learn from here. Greger?
Thank you very much, Jacob. Yeah, so the topic here is explainability of business decisions. And indeed, as Jacob said, focusing specifically on decisions where we use both business rules, decision models, and machine learning models in combination. This is more of a work in progress, not yet any product implementations. This is actually research I've been doing with local university colleagues here in south of France at the Université Côte d'Azur, and also at INRIA Research Lab. We just presented this in form of a paper last week at the ECML European Conference on Machine Learning. So this is kind of hot off the presses, if you will. What I'll do today is a kind of less academic and more of a conceptual. So I will try to keep, there will be some math, but I will keep it to a minimum and focus on explaining the concepts, and then we can have some discussions around this and the limitations and the potential benefits of this approach. So I'll go very quick on explainability. We've covered already on Monday, and several other speakers as well. I'll talk a little bit about the current approaches that I've seen at least being used to provide some sort of explainability for decision management, our new research approach, and then some limitations of that as it is work in progress. And I would love to have some feedback on this and some discussion around the feasibility and the benefits of this. So why explainability? As I mentioned on Monday, we are increasingly doing high-stakes applications across credit and lending, employment, promotions, admissions to educational institutions, and so forth. So as we do more and more decisions that have a high impact on the individual and on the outcome, we are more and more concerned about how these decisions are made because it has a high impact. And as we also talked a lot about on Monday, in particular, Alan's presentation on the European AI Act, the proposed legislation for grading applications using AI from minimal risk to unacceptable risk. Many of the business automation use cases we consider and we work with, of course, are probably going to be high risk or close to it, which means that there has to be some level of transparency and explainability for these applications of AI to be acceptable. So that's kind of a lot of the context. But in general, I just think that a lot of the explainability and transparency technologies we are considering is just useful for understanding and trusting our own systems and our own decisions, just purely from an organizational point of view. This is, after all, right, one of the long-standing benefits we've had with business rules management systems all the way up now to decision intelligence, that we have transparency, we have policies that are expressed in a readable and understandable fashion, right? So we shouldn't let go of that benefit of our approach just because we are including machine learning. So just as a reminder, for those of you who might be watching the recording on Monday, I talked a bit about model transparency, meaning various ML model types, such as from decision trees to rule sets and scorecards. So if you're because that is one aspect, one approach to bringing more trust and transparency into our decisions. Today, I'm going to focus on decision explainability, which in my terminology means we're trying to understand a specific decision, not the whole model, just the reasoning or the causal behavior behind a specific decision. So that is the context. There's a number of different use cases where we are combining machine learning with business rules. And as you all know, typically the machine learning is used for predicting something, a likelihood, a probability for something to happen, typically in the future. How will a customer react? Is this a fraudulent claim? What is the likelihood for that, etc. And the business rules are then used to interpret those predictions, add policy, and make a decision, right? Should we actually refer this fraud for investigation? Should we approve this mortgage application, etc.? All the classical use cases. I'll use today a same use case as I used for transparency on Monday, which is a telco retention example. So I'll go through that, but of course I would treat this a bit different today because I'm talking about explainability for a specific retention offer, not the model as a whole. But as a recap, what we have here on the right-hand side, we have a set of ranked retentions offers. We produce a set of ranked retention offers. We are then on the left-hand side calculating a budget. How much do we want to spend on retaining a customer based on a churn estimate and a customer lifetime value estimate? And with those two things, the budget and the costs of the different ranked offers, we can decide which retention offer to make, something that is within the budget, of course. So that is the kind of overall use case or the example I will use today. In general, when we talk about the explainability, there are, depending on the persona, we are typically looking at different things. A data scientist building a model will use the typical data science tools from notebooks, visualization tools, etc., to ask, is this model working correctly? Usually this is during training and model debugging time. A business analyst consuming a model that has been built from data will ask, how is this predictive model behaving in conjunction with my policies on my cases? Is it behaving as I expect it to be? Is the churn risk high for cases where I think the churn risk is high, etc.? Is it handling outliers correctly? A caseworker, someone being given a recommended decision, for example, in an insurance claim situation, might ask, why am I being recommended to reject this claim or investigate this claim? So that's a slightly different use case. And an end user, an individual receiving a decision by a bank or a retailer or a government institution might ask, well, that wasn't the outcome I wished for. I wanted my mortgage approval to be approved, not declined. How can I get to a desired decision instead of the negative decision that I received initially? So there's various use cases around explainability for a specific decision. Not all use cases need explainability in the same degree. There's use cases I think that are where explanations can be more nice to have, and there are other cases where they are more critical or fundamentally necessary. If you're looking at some of the nice to have use cases, I think advertising, some types of loyalty programs, product recommendations, maybe some cases of fraud detection. I think here, to the extent we do need explainability, it's more to provide a good user experience for our end customers. You can see this today, for example, on Facebook, have some way of explaining why they're serving certain ads to you. Amazon, similarly, when they're doing product recommendations. So I think there are cases where it's nice to have explainability because it helps with the user experience. There are other cases where we are talking about regulations, and we talked a lot about that on Monday on the AI Act. And then there are cases where I think that the acceptance of a system will not be good unless you have some form of explainability. A medical doctor are much more likely to trust a recommendation or a diagnosis or a drug prescription if there is a rationale behind that recommendation. There are many, many other use cases, but I think in some cases they are more critical than others. So that's on basically sort of like what the use cases are and why we need explainability. I want to go through quickly 3 or 4, I think it is, of the typical approaches, at least I have seen, there might be others, but that I have seen that we have used traditionally in decision management to provide some explainability or rationale behind our decisions. And this, by the way, if you look at the right-hand side here, I think that there's a lot of similarities, whether we are trying to explain a decision model or whether we're trying to explain a process model. In the bottom example here, for example, this could be a case where we are doing a mortgage application or loan application, and as part of that, we're calculating a risk score, and it's a similar situation there. We want to give the case officer some level of rationale for this decision. The current, but on the whether it's a decision model or a process model, in many cases we want to explain the entire decision, at least, especially if we are presenting that to an end user or a customer, not just the individual pieces, not just using internal terms and data that we might not want to present to the end user or the caseworker. The approaches that I've seen, I'm going to go through them quickly one by one, are rule traces, reason codes, attribution methods, and counterfactual explanations. And they all have their own pros and cons, I would say, depending on the persona we're targeting with this explanation and the approach we want to take. So rule traces, I think, is the most common, approach to giving some insights into what happens in the execution of a decision, at least when it's based on business rules. And we can extend rule traces also when we're doing ML predictions by just basically including the predictions from the one or more ML models we have. On the example in the right-hand side, you can see that in the bottom, we have the run history. That's basically the trace. Each blue headline here is basically a decision node in our decision model. And you can kind of zoom in and open up and inspect what's happening. And on top here, we've aggregated and printed out some of the machine learning models. We have a lifetime value model. We have a churn model. So we can kind of see what scores we got from the various machine learning models. So that's a kind of a rule trace. There are sometimes more or less interactive, but the basis for them is basically that it is a procedural explanation. What are the steps? What are the chain of rules that triggered? So it's not fully end-to-end causal, meaning it doesn't give a causal explanation from the inputs to the output. It's more of these are the steps that happened that led to the output. Rule traces doesn't give you a contrastive explanation. And by contrastive, I mean, how do we get to a different outcome? My mortgage was declined. How can I have it approved? It doesn't give us that. We can play with the rule trace, try, in like a testing what if kind of thing, but it's hit and miss largely. And there is no certainty that our exploration or testing with this decision model actually give us the simplest way to get to a different outcome or the cheapest one. So it's not great for contrastive what if kind of analysis. There's no attribution, but I mean for the input variables, in this case, income and age and so forth. There's no attribution to how those individual variables and the values we inputted to those variables, which one mattered the most and which one mattered the least. But nonetheless, this is good primarily, I would think, for the rule author, the business analyst, to debug and understand how the different parts of the decision model and the ML models, how they interplay and interact to come up with a specific decision. It's, as I said, it's obviously not great for end users, in part because there's a lot of internal information here, and we might have model privacy issues and so forth. So it's not great for an explanation for end users. So that are rule traces. The second one, which is very common, at least in some industries, is there are reason codes. and I put them in the category of other constructed explanations. Reason codes is used very heavily in it's part of scorecards, for example, but you can also envision just more custom reason codes or constructed explanations. So in the bottom right, it's very feasible, of course, to have a regular if then else rule that not only produces returns a value or a decision, it also returns a message or an explanation to give context and rationale for that decision. It can be as simple as a text string or a list of text strings or whatever. It's very similar to how a reason codes or a set of reason codes might be processed in a scorecard. Limitations of this is, of course, that this actually requires intentional design. The rule author has to build up these reason codes and decide how they should be aggregated up the tree, if you will, when the decision is being processed. It doesn't give us contrastive explanation, at least not directly. Of course, you can look at a set of a reason code from a decision and say, there's maybe the income or the debt to income ratio is the reason that popped up as a reason code. That might be one of the issues why we were not approving this mortgage, for example. But directly, you can't ask a reason code how we get a different outcome. Similarly, we can't get attribution from reasons code, not directly. We can't get income was valued this much versus age and so forth. So traditional attribution methods traditional attributions aren't being given by reason codes. Finally, but this can be useful, right? I think it's one of the better and most common explanations I've seen for end users. You can provide a, or at least for caseworkers, a domain-specific explanation for end users and caseworkers. You can also use it for some types of reporting and decision analysis. You can look across a set of test cases, for example, a simulation, and see in how many of those cases were a certain reason code generated versus another one. So you can sort of see from the reason codes, you can do some basic level of analysis on that. The third one I want to mention is actually an attribution methods. And by attribution methods, we are giving a weight to each input variable, like age and income, education, etc., in how much that positively or negatively impacted or contributed to a specific decision. And these are very common, or has been very common over the last, I think it's probably almost 10 years now, in the machine learning community. And LIME and SHAP are probably the two most well-known methods for at least model-agnostic attributions, meaning they work on any type of a machine learning model. It can be a neural network, can be a decision tree, anything. And we can, of course, apply them on the whole decision as well. That's certainly feasible. The way they work, these methods, typically, there are variations, but typically they are sampling based. So they take a prediction. You can look at the right-hand side here. They look at the prediction and they sample the neighborhood around that prediction. They basically go around, typically in a spherical fashion. And they see what the predictions are happening there. And then they fit a simpler, transparent machine learning model, typically a linear regression. And the weights of the coefficients of that linear regression becomes the weight. So it's a local approximation, essentially. So we say that LIME and SHAPs provide a locally correct explanation, but it's only local. And it all depends on how you sample and how wide you sample. That will determine the slope of this curve, and that determines the weights you get for the various variables. So, but it does give you weights for the actual input variables. It's all model agnostic. It's just focusing on the inputs and the outputs. It's not revealing anything on what goes on inside the model, the decision model, or the prediction model. It doesn't give you contrastive explanations, really. It is just very locally, here are the weights for the various variables. It can potentially be expensive, especially if you apply this at the decision model level, because typically, I think the default value for Lime, I believe, is like 5,000 points around a prediction. So you do a sampling with 5,000 points, and that means 5,000 invocations to the decision model. So that could be expensive depending on your decision model and your situation. The main problem, though, is that it turns out it's not robust, especially not for decision model, at least not what we have seen in our testing and our investigations and analysis of these methods. And it's two reasons, actually, or two reasons in combination. One is that the policy rules we apply, the business rules we have in our decisions, often cause kind of sharp corners and non-linearities. We might say, for example, that age has to be, to rent a car, age has to be at least 25, and you have to have a valid credit card or whatever, you know. That's a sharp corner. It's not a smooth, probabilistic, statistical thing. It's a sharp corner. These tends to, and if you sample around those sharp corners, the weights you get, the slope of this curve can just vary wildly. So it's very unstable around nonlinearities, and the sampling issues themselves contribute to that issue, but the sampling itself also contributes to a situation where if you're far away from the actual decision boundary, if this scatter plot here, shotgun of sampling predictions, if that is way inside the boundary, far away from the boundary, you tend to get weights that are kind of all equal. You get equal weights for many or most of the variables, so they don't tell you anything. So there are some limitation issues with Lime and SHAP style methods, especially at the decision model level. That said, though, it is maybe better than nothing, if you will. If you're careful about how you apply them, it can be it's model agnostic. You can pick up these methods and use them at an ML model level, which is most commonly done, or at the decision model level, and they will give you something. The problem is whether you can trust that or not. The final method I'll talk about is counterfactual explanation, which I already mentioned, which is that you want to search for some changes, typically the smallest changes, to one or more input variables that would generate a different, more desired outcome. And I've depicted this on the right here. You have a prediction that is a declined mortgage, and you want to get to an approved mortgage, and it's basically finding one set, what sort of changes to your input variables that can generate to get you to a point where you have an approved mortgage. The good last year was a good presentation on this from Mortari and Sonka from Red Hat. So I recommend this one if you haven't seen it. In the Trust the AI toolkit, they talked about how they do it in Red Hat Decision Manager. There are also many toolkits for counterfactual explanation, including ours at IBM. We have an IBM Explainability 360 toolkit, and in there you'll find some variants of counterfactual explanations. But there are many such methods in the community of machine learning today, which you can then, of course, apply to the, in some cases at least, to the entire decision model as well. Problems and limitations with counterfactuals. Well, you have, as I mentioned, for transparent models on Monday, you have the same Rashomon effect for counterfactuals, which is that there might be many counterfactuals that are equivalent. And how do you find one that is the best, or how do you sort or compare them can be an issue. Again, you get no direct attributions to the input variables. You don't get any weights. There is no direct sensitivity. You don't know how far you are away from a decision boundary or a different decision. They can potentially be computationally expensive, right? Because you are doing essentially some kind of search on top of a decision model. So it's similar in that respect to how the sampling is done, right? So potentially computationally expensive. But it's great. It can help you actually answer this very fundamental question: how can I get a different, more desired outcome than the one I got? So I think it's a counterfactual explanations is a very valuable tool if you can have it in your arsenal of tools for better explainability around decision models. So those are the 4 methods I've seen: rule traces, reason codes, attribution methods like LIME and SHAP, and counterfactuals. Just a summary of those methods, right? I would say that the common approaches are rule traces for business analysts to understand and debug procedurally what's happening in a decision model. Reason codes for end users, such as those in scorecards, but also custom ones. LIME and SHAP are very popular in the machine learning community. We haven't seen them as much applied in the decision management community, but it's worth testing if you're careful, I would say, because pay attention to robustness, potential robustness issues there. Counterfactuals, I'm not sure how much they are used, but I think it's something that is very valuable, and we should probably look at those more in our community. Limitations I mentioned: rule traces are mostly for testing and debugging. Reason codes require expertise to build and construct. Maybe not more expertise than you need to build the actual decision model and the business rules, but nonetheless, it's another layer of complexity. And LIME and SHAP are not robust. And we are essentially missing reliable methods for attributions, weights, and counterfactuals. I would say that's kind of a hole in our arsenal of tools currently. So what I want to talk about in the next then is sort of an approach to, or we started looking at some of these problems and to see if we can make some progress towards solving those problems, providing attributions for the input variables, and also potentially looking at counterfactuals. And we've been looking at this, and we came up with an approach that we call SMACE, and stands for Semi-Model-Agnostic Contextual Explainer, like many other acronyms. Model agnostic, by that we're referring to that we are actually allowing any type of machine learning model. So we're applying, as part of this method, we're applying model agnostic tools like LIME and SHAP as a piece of it, as you'll see. But it's also, so it's model agnostic for ML, but it's model aware for the business rules. We are trying to reuse or capture and leverage the symbolic semantics of the business rules. We're not treating the business rules in our decision model as a black box. We are really using the individual rules, as you'll see. So that's why we call it semi-model agnostic, because part of the decision we treat model agnostically, and part of it we don't. Contextual means that we are explaining in the context of the inputs of the decision. We are not revealing anything of the insights of the decision. So that's that. What the questions we'd like to answer are the ones I've already talked about, essentially. What input variables contribute most to in a positive or a negative way to a decision? So these are the weights or the contributions. I use those interchangeably. And for an end user, that might be, what caused this decision? Was it my age or my income or whatever? How sensitive is the decision to changes in inputs? Is it robust, or could a small change in income change the output in a specific way or unpredicted way? What are the different closest outcomes, contrastive or counterfactual outcomes I could get? And of course, we talked about this already in the terms of a approval of a mortgage, for example. Regardless of these use cases, what we need to have is we need to have attributions for our input variables. We want to focus here on explaining the decision in terms of the values for the input variables for the entire decision as a whole, not revealing anything of the innards. We want to be able to have multiple machine learning models with different data distributions in this, and you'll see why this matters soon. We want to, of course, account for the interactions between the machine learning models and the business rules in the decision model. So it has to be kind of the interplay between the predictions from machine learning with the business rules has to be accounted for. And in the rest of this, I'm going to focus primarily now on the first one, basically. How can we get attributions, contributions of weights for the variables of the input? The other ones I'll reflect on in the end, but basically I want to focus now on the technique we apply for the first case, right? How do we get feature weights or variable weights? So as a recap again, here's our decision model with our ML-based model at the bottom. And I'm going to take this part of this one and simplify it for this example. So we're going to just look at a simpler case. We still have our two machine learning models, the customer churn and the customer lifetime value. This is based on the data on the customer and the data on the subscription. But I'm simplifying it, so we have just a simple, the customer lifetime value is basically any dollar amount, whereas the probability for the churn is expressed as a probability between 0 and 1. The main rules I have in my retention often, and this is a simplification, there's no budget consideration anymore. I'm just saying that if the churn is greater than 30%, the churn probability is greater than 30%, and this is a high lifetime value above 7,000, then I want to give a 20% discount as a retention offer for this customer. If it's above 0.3 in churn, but between 3,000 and 7,000, I want to give a 10% discount, etc., down to just giving a satisfaction survey or no retention offer whatsoever. So this is kind of my business rules on top of these two machine learning models. Here's some data. This is actually actual data from the data set we've used to train the churn and the lifetime value models. And what you're seeing is on the x-axis, the churn probability going from 0 to 1. On the y-axis, you're looking at the lifetime value in dollars, going from about 0 to 9,000. And if we look at these retention rules that we have, or these retention offer rules visually, you can see that we have a boundary here of 0.3 for churn. Below 0.3 in churn, we give no retention action whatsoever. Then we have an area of the decision space here where we give it 20% discount, and that is when the lifetime value is at least 7,000. And then we have another area where we give it a 10% discount, where the lifetime value is about 3,000, and then we have the satisfaction survey in the bottom. So this is just a visual view of how these rules look in the decision space. And again, some of the questions we want to ask is how stable is this decision? If we get a specific prediction, what input parameters contributed most positively or negatively for a specific decision? And this is the one I'll focus on. The counterfactual explanation will be something like, how could I get a different desired outcome for a specific customer than the one I got? How could I move up to either the 10% discount or move right to a satisfaction survey as an outcome? But and again, I'm going to focus on the middle one, right? What input parameters contributed most positively or negatively? And here's the main slide, and I'm going to break this down for you. Here's the main slide of our method. It's basically 3 pieces. The first piece is that we use machine learning attribution-based method. We use LIME and or SHAP. We can use either of them to look at the machine learning models one by one. The second thing and this gives us weights for the variables for each model, and I'll come back to that. The second thing we do is that we take all the business rules that we have on top of the machine learning models, and we do a geometric interpretation of them in the decision space. We look at them to look at how far away they are from decision boundaries and how much contribution we can assign to them based on that distance. So that's the second piece, which I'll go through as well. And the third one is then, how do we combine that? How do we aggregate the contributions from both machine learning models, the weights we get there, with the weights we get and the contributions we get from the business rules side? So I'll come back to that as well. So let's start with the number one, right? The Lime and SHAP for machine learning based weights. So what we want to have here is basically a weight for each feature for each model. So if we have 10 features, they are represented by a index J here. If we have 10 features, age, income, etc., and we have 2 models, churn and lifetime value, for example, then we're looking for 20 weights, right? With 1 weight for each variable for each model. And so it might look something like this. We have our input to our decision. As an output, we get churn equals true with a confidence of 0.78. Then we apply Lime and SHAP to this. And Lime and SHAP, they do their sampling around this prediction and comes up with basically what we call feature weights or contributions. So you can see they can be any value. They can be positive or negative. It depends on the distributions of the data for these models. Some cases they're negative. That means they're contributing negatively to the churn. So in this case, for example, the number of children and the status and the gender all contributed towards churn being true, whereas the long distance input value contributed negatively. So if the long distance had potentially been much, much higher, even higher, then there might be a churn equals false as an outcome, right? So this is how to look at this. It's with the relative contribution between these feature weights. So these are our weights, WJM, right? The weight for variable J for model M. And in our cases, we need to do this for all combination of models, for all models and for all features, all variables that we have. Then there's a second step. I'm not going to go through details, but basically we need to normalize these weights because the distributions are very different for the data. So lifetime value can be, as you saw, anything from 0 and up, right? They've measured in dollars, whereas the churn is measured as a probability between 0 and 1. So to be able to compare and aggregate feature weights from churn with feature weights from lifetime value, we need to normalize them. And what we do is basically we normalize them based on the sum of the absolute values of the feature weights. We could use other ways of normalizing as well, but that's what we do. And after we've done that normalization, we have W hat JM. We basically can compare these weights. We can kind of add them and so forth, right? In a way we couldn't do before. So that's the first step, using off-the-shelf Lime and SHAP methods for getting feature weights for each of our machine learning models and each of our variables in those machine learning models. So that's step number 1. Step number 2 is going to be the geometric interpretation of rules. So remember, we have this view here. And if I just shade the background a little bit, so we can look at this, the geometry of these decision boundaries. What we're looking for here is a contribution for the variables, the input variables, based on the rules. And the rules are here the decision boundaries, right? LTV is greater than 3,000, LTV is greater than 7,000, churn is greater than 0.3. That's our decision boundaries. And you can see there's 3 or 4 areas here if you include the no retention action, right? So let's say we do have a prediction here, and let's for one specific case, we get a churn which is 0.55 and a lifetime value of 3,900. So that's a specific customer, say. What we want to have in our method is that we want to assign a high contribution for a variable that is close to a decision boundary. When it means it's highly sensitive. If it just moves a little bit, we might get a different outcome in our decision. So we assign a high, in this case, the lifetime value is 0.55. Sorry, the LTV is 3,900 for this prediction. And there is a boundary at 3,000. That's relatively close. So we would give this something close to 1, maybe 0.7, 0.8, 0.9, or something like that. So closer to the boundary, we give it a higher value. If you're on the boundary, you'll get 1 as a score for R. Similarly, for churn, we're a bit further away from the boundary. In the case of churns, we'll give it a lower value, still between 0 and 1, probably around 0.4 or something like that, 0.3 in this case. So, so that gives us an R value for each prediction, meaning for each machine learning model, based on the rules, the boundaries of the rules that are closest. And we calculate this for both input variables and predictions. So in this case, I just had churn and LTV, which is both predictions. But we would do the same, of course, if we have rules expressed directly on income and age and so forth. So we do have these RJs for the input variables and RMs, and these are the contributions from the decision boundaries representing the rules. So that was step number 2. So we have our feature weights from Lyman and SHAP on the left-hand side. We have a geometric interpretation of rules, which I'll give you the RJ and RM contributions. And now we want to put these two things together. We want to take all our feature weights from the machine learning models. We want to aggregate them up, combining it with the contributions for the rules, from the rules, and weighing them in a sensible way. And this is what we do in step 3. And the end goal is that we want to have EJ, and EJ is the contribution for a variable for the entire decision. And the way we compute each, so there will be an EJ, right? There will be an E income, there will be an E age, it will be an E credit card, etc. Or payment method, I guess it is. So for each variable, we'll have an E value. That is our weight, essentially, for the whole entire decision. And the way we compute this is that we take RJ. Remember, RJ is the contribution for feature J for the rules, right? It's a decisions. It's a distance to the decision boundaries, essentially. The closer we are to the decision boundary, the higher that will be. And then we sum that up across all machine learning models and all the weights for all the machine learning models. So in this case, we have 2 machine learning models, LTV and churn. That means we will be summing up all the weights for churn and all the weights for LTV. And in each case, we multiply that weight from Lyman and SHAP with RM. And RM, as you remember, is the closeness of that prediction to the boundary we're looking at. This means that intuitively, if the LTV prediction we did, is very close to decision boundary, that means RM will be high, close to 1. That means that we will weigh highly the feature weights from that machine learning model, from the Lyman SHAP calculations, which means that we give more emphasis to feature weights coming from machine learning models that are close to decision boundary and thus are close to having a significantly different outcome. That also means, conversely, if we have a prediction of churn that is 0.001, there's very, very, very low churn risk. It's far away from this 0.3 boundary. We will pretty much ignore these weights coming from churn because they are not relevant. They don't impact the decision very much. So this is kind of at conceptual level. That's what we do. The output then is, of course, contribution for all the original input variables only. The internal computations of churn and LTV or anything else is hidden. So this makes it suitable, for example, for a caseworker or an end user or something like that, who is not a business analyst having access to all the rules and so forth. It's really input output, and it's based on feature contributions or weights for the input variables. The second comment is that as I said, we're scaling the feature weights on the machine learning models by the sensitivity of that prediction, as the rules indicate and the decision boundaries indicate. So that's in essence the method. And through this approach, we're able to combine, aggregate both machine learning based feature weights as well as the business rules in the decision model. So that's it. That's the that's the good part. Now for the bad part. This is work in progress. We have, I would say, barely scratched the surface. That we have currently lots and lots of limitations. But just to illustrate what we could use this for, of course, here this is a little bit of a mock-up, right? On the right-hand side, you have the rule traces and so forth. We can still have that, of course. But in addition, we could have the left-hand side, which is basically feature weights for all the variables. And we could selectively, optionally include internal variables if you wanted to, but we would have the option of just expressing the contribution based on the inputs and the outputs. We could also have some counterfactual, contrasting decisions, meaning answering questions, what changes are required for a different outcome. If I want to have the 10% discount offer for this customer, what would I need to change? What would the distance be for an estimated income? I didn't show you the math for this. It would be different, but something like this would be possible. We could also rely, whether we want to or not, on internal versus external variables. So this is a bit of what we could do with this. Now to some of the limitations, and there's quite a few of them. We have currently, for the theory and the implementations we made, we have another limitations. There's limitations on the types of rules we can express. Currently, we just consider one-dimensional rules, a variable xj greater or equal to constant. Very similar, by the way, to the rules we get from when we do rule learning, traditional rule learning using Ripper and so forth. We talked about that on Monday. So that kind of format we support currently, and the point is that these rules give us decision hyperplanes in space that are orthogonal to the axis. We don't support nonlinear expressions or like multiplications and divisions between variables in the clauses in our rules. We don't even support disjunctions yet. We don't support negations, although this could be trivially made typically. We don't support categorical variables yet. So these are a lot of things we haven't considered in the rule expressiveness currently. Some of these are relatively simple to handle. Some of them could be more complicated at the mathematical level. Remember, what we need to do in essence is just calculating the distance from a point in space to the decision boundary. And some of these different rules will basically change the space, right? So a disjunction will give us a non-convex decision space, for example. Categorical variables will be different than the convex hull we have currently with our simpler rules, etc. So there's just different math behind calculating the distance to a boundary. We also have some limitation on the decision model itself. We currently can't use output from one node to another. We can't use output from one machine learning model to another machine learning model, for example. This is not necessarily a big limitation or a big difficulty, but we haven't implemented or considered the math for that yet. So we have some open questions also around have we fully isolated line SHAP from the sampling issues and the nonlinearities, which we talked about in the beginning through our method. In the way we use line and SHAP internally, are we perhaps still exposing ourselves to some issues there? It's unclear. And the general question is this, which is all the limitations on the left-hand side. Can we cover all types of business rules, right? We have many business rule systems today or decision management systems today. We have a lot of expressiveness, right? Almost procedurally. We talked about this yesterday and today. Can we get meaningful output of an explainability system like this without capturing all the procedural complexity that we might have? So that's a few things we are looking at. But just as a summary, I think there's a going back to not ending on a negative note, but ending on a little bit more positive note. I think that even if we can't expand this system to cover all the complexities and the expressiveness of rules, there are some takeaways here, I think, that we found that are probably generally applicable. Number one is, of course, number one here, right? The top left, we have a way now of using Lime SHAP internally in the decision model to get feature weights. And we have a way of normalizing those feature weights between multiple machine learning models so we can actually aggregate them or compare them. So that's contribution number one, I think, from this research. Number two is on the top right-hand side, the geometric interpretation of the rules. It makes sense to consider decisions to a boundary. It might be harder to compute with full expressiveness of rules, but we can also potentially do some types of approximations. Right? It doesn't have to be exact necessarily. The third contribution is just the fact that we have a way now of aggregating up weights for variables through the decision model, right? From the leaf nodes, from the ML predictions, all the way up through the business rules, and weighing them in a sensible way, so that a prediction that mattered a lot for the outcome of the decision gets high weights, versus a prediction that mattered just a little bit or not at all are toned down when it comes to contributions to the variables at the end. So these are, and I think those are kind of takeaways that can be used even if you have a simpler approach to computing your explanations for your decisions. So I think that's all I had, actually. So happy to take questions or comments on this.
We only had one question from Alan, and then you answered the question, I think, on the next point. So there weren't any questions. Although Jan just popped up with a question, just saying, comparing to general machine learning models, shouldn't DMN models be easier to explain because there's less uncertainty?
Okay, I'm not sure I understand that question. Can you expand on it? Or
Jan, do you want to unmute? And there we go.
It's just a wild question. In DMN, we often have we always have very deterministic rules and so on. There is no uncertainty. There is no real machine learning. So maybe it's a little easier to explain. If you look at the boundaries, the boundaries are very static. It's not dependent on the data set.
Yeah. No, that's true. So the whole the business rules are well defined, right? The boundaries are well defined, and that's what we do. I mean, we interpret those boundaries exactly when we compute the distance to a boundary. So that's what we try to do. The problem is that some of these business rules, like a disjunction, right? If something or something in space, that gives you two different convex hulls, if you know, that gives us two different decision spaces. We need to be able to compute the distance from one to the other, necessarily, right? Yeah. So the business rules are well defined geometrically in the decision space. It can just be difficult to do the computations we need to do. Computing the distance to a boundary, for example. But yes, it's very well defined, and that's the core part of what we set out to do. We wanted to preserve the business rules. We wanted to leverage the fact that our whole decision model, excluding the machine learning, is transparent. It's well defined. It's symbolic, right? We didn't want to take so if you use Lime and SHAP on top of the whole decision model, what you're doing is you're using a probabilistic method to find something out about the declarative set of business rules or a declarative decision model, and that's a waste of information. So that's why, that's the whole kind of how we got started. Can't we use some of this information we have from the business rules when we try and explain the whole model?
All right, thank you.
Greger, I want to make a comment. You have IBM, you talk only about machine learning and business rules. IBM has one of the best optimization engines in the industry. And I'm a little bit surprised that you're not bringing it at all this. For example, when you said for explanations, we are doomed to try and fail different loan amounts, for example, and the user keep rejected. Yesterday, for first day when Alan presented conversational explanations, one of the way to address this, for example, in this particular way, not to force user to provide exactly required loan amount, exactly required loan term. They can tell, I need, for example, a loan between 50 and 70,000 and a loan term between 36 and 72 months. Can you give me the maximum possible loan? And in this moment, it's not try fail. It's actually you're running a little bit smarter engines that we have today. And this engine provides you with particular solution and quite quickly and explains really why it happened.
Yep. But that's very, I think that's, I haven't done this myself, but you're absolutely right. We could apply a constraint programming solver or maybe even a mathematical programming solver on top of this, right? And I think this is exactly what the Red Hat folks presented last year. I linked to this video. So Matteo Mortari and Zonka, they actually use the Opta planner, I think the solver is called, on top of a decision model in Drools or Red Hat. So I think that is perfectly an approach that is also worth exploring, of course.
Yeah, we're talking about this for many years, but optimization still, everybody pushing optimization aside. And I think it's finally, maybe we should bring it in context of explainability. Anyway, thank you very much. Very interesting. And
yes, thanks, Greger. We need to wrap up now. So.
Okay, thank you very much.